All right, so recording is rolling. Welcome to Monday, January 10. We're starting next topic today. Actually, the topic we're starting today, which is simple harmonic motion, periodic motion, also teach you guys about wave motion, is the last official topic we have to cover for the AP exam. But like within a couple of weeks from now, we'll have covered every single thing that is going to show up on the AP exam. And we're going to kickstart this with a lab. But before we get to that, you guys have clicked on the front of your desk a packet that looks like this. You guys see this one? There's chapter 13 puzzles, and then there's chapter 14. I think chapter 13 was simple harmonic motion of waves, and 14 was sound, but I think how it breaks down. Does anybody not have this? Right. And we're doing this the same way I've been doing these all along, is that I'll assign these problems to you, and then I'll go over these in class so that you'll for sure have them all, as long as you're paying attention, taking notes. Right? Oh, and also, of course, you guys have an AP Classroom. So here's the assignment. You guys have got AP Classroom Unit 6. This is the last official topic. Try that due Tuesday, January 18th. You guys do know we have a 3-day weekend coming up, right? Because of Martin Luther King Day. Right, so you guys come back from that. We'll hit this. I'm pretty sure we'll have by this point covered enough information that you should be able to handle these. Right? These problems have been open a few days now. Right, then that packet you guys just pick up, chapter 13, 14. Right, here's the main homework assigned from this, and then also bonus homework, just like we've been doing for most of the fall semester. So keep doing that. Worked out pretty good. All right, so you guys got this far? And then I'll upload grade columns and focus that have these numbers listed. This is being recorded right now, so you guys will have access to this video, and you guys are seeing them right now. Okay. All right, so we're trying to figure out something about periodic motion, right? Something about simple harmonic motion. Well, let's start with this pendulum lab, and maybe we can figure out a lot of what governs the motion of, say, a pendulum scientifically through a lab. And then later on, when I show you guys the textbook formulas, you'll be like, oh, yeah, I remember like doing this lab, and we got exactly those results, that sort of thing. Now, original plan was to demo this for you guys and then send you back to the lab area and have you guys do this, but we're not going to do it that way today because yeah, COVID is raging through pretty hard. So we're going to do this lab the same way I did the entire quarantine year like last year, which is I'll do sort of demo style. I have a pendulum set up right here. I'll turn the camera for everybody watching the video, and then I'll just do this step by step with you guys, and then we'll have the same data by the end. I mean, there are some advantages of doing it this way anyway, so anyway, that's how we're doing this. Okay, so I'm looking at this pendulum. All right, give this thing a swing over here. So if you're in class, you can see this pendulum swinging back and forth. Right. Okay. I wonder what physical variables are governing the motion of that pendulum. Okay. So I thought of some that might possibly be involved. Okay. Like maybe the mass of this bob. Okay. Like if you increase this mass, say from 100 to 200 grams, okay, how could that maybe, for example, affect the time period? Something like that. Or maybe there's a relationship there. Okay. Hey, let's do some quick hypothesizing. So you take that exact example. If you double the mass of this bob from 100 to 200 grams, side note here, we are assuming that the string itself is either massless or has negligible mass, so like all the mass is concentrated in this bob. Okay? So if you increase this bob mass, is that going to increase the time period? Or say it slows it down? Is it going to decrease the time period, which makes it swing back and forth really fast? Or maybe there's no relationship. Maybe you increase the mass and it has no bearing whatsoever on the time period. Let's see, show of hands what you guys are thinking. I mean, it's going to be one of those 3 hypotheses, right? So how many of you guys think if you increase the mass of the bob, that will increase the time period? It's going to slow it down. Slow it. Okay. How many of you guys think if you increase the mass of the bob, it's going to decrease the time period and speed it up? How many of you guys think that these are not related to each other at all? Okay, I think most of you guys are saying that last option, but there were there are votes on any of those options, so we'll figure out this scientifically. Okay. next possible variable, ooh, how about the starting angle, starting angle theta? So you started at 20 degrees, and then you up that to 30, 40, 50 degrees. As you make that angle bigger, 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 what's that going to do to the time period? Right, so same three possible hypotheses. I'm going to think if you increase this angle, say from 30 to 60 degrees, that will also increase the time period. It's going to slow it down. Who thinks that? Who thinks if you increase this angle, it's actually going to speed it up and decrease the time period? And who thinks that these two variables are not related to each other at all? Like it can change the angle and the time period is just whatever it is. Okay, so again, I'm seeing votes on any one of those. So we'll again do the science, but yeah, any of those are possible. Right? How about the length of the pendulum? Right. So if you make this length bigger, 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 what's that going to do to the time period? So let's just have the same basic hypotheses. So if you increase the length, will that also increase the time period? Let's just say slow it down. How many guys think that that would be true? How many guys think that if you increase the length, that will decrease the time period? They go really fast. And how many guys say that there's probably no relationship between those two? Make it longer and the time period is whatever it is based on other things. Okay, so again, I'm seeing votes on any of those, and you know this one. We're about to find out. You know what? Before I get rolling too far, there actually is another physical variable that is in the textbook equation that ends up being important that I did not write up here. Who thinks they might know what it is? Yeah.
Gravity?
Gravity, yeah, gravity field. Yeah. So here, I'll go ahead and turn the camera so that if you're watching the video, you can see this pendulum. I just get the pendulum in the, yeah, okay. So here's what this looks like on Earth. Now, yeah, gravity field, that would be really hard to change in a like a high school physics lab. I guess if you're really tricky, maybe you could set up like a merry-go-round, like centrifuge sort of setup and sort of, right, that would be really tricky, right? Let's say we took this to the moon. Guess what would you expect to see on the moon? Would you expect to see exactly the same ocean? Do you guys think you would see something like, no? Or do you guys think you would see like, probably that last option, right? Okay, so maybe going back to Earth from the moon back to Earth, that would be increasing the gravity. It looks like this thing speeds up, that would decrease the time period. Okay, so maybe something to do with an inverse relationship between time period and gravity, which we're not going to test for, but keep that in the back of your mind when you see the textbook equation, like, okay, I see how that factors in too. But we do have these other variables. So switch the camera back. All right. You guys have a lab page, which I'll tell you guys to set this lab a little bit different in the past, and then I amended this at the last minute, and could have designed this a little better, but this is gonna work for us. Okay. Does anybody not have this lab page? Everyone have this? Okay. So on one side, we've got some tables. On the other side, we've got space for some graphs, and this is eventually going to lead towards this conclusion. Now, so far, my classes today, we've got about 90% of this finished, and we've just got to finish like one graph to get the answer. So we'll save the tail end of this lab for tomorrow, but we can get all the data today anyway. Okay? But you know what? It looks like we're juggling 4 different variables here, right? 5 if you also include the gravity field. So how are you going to juggle like 4 different variables? Well, probably the same way that we've run into the situation for like many labs in the past, right? We have like lots and lots of variables going on, and that's to just create one is independent and one is dependent and keep the other ones controlled, right? And then do several experiments. Okay, so that's what we'll do. Like for example, you change out the mass and see how does that affect time period, controlling for theta and length, right? Okay, that could be one of 3 experiments, and then make theta independent variable, then make length independent variable, just one at a time, controlling for the other 2. Right, so we're going to relate everything to time period is how this particular one's set up. Right. If you look at these tables, at a glance they all look the same because they all have the same columns, but if you look really close, I put some hash marks in some of these to say like they use the same number all the way down, which means that variable would be controlled. That's like the intention of this. Right? So this first table, looks like I want you guys to use the same mass all the way down, which means that mass would be controlled. Same thing for the starting angle, that would also be controlled. Okay. Okay, but length is an open column. And okay, so that might be, think of it like an independent variable, call it IV, independent variable. Okay. And somehow that's going to affect the time period of string. Oh, but there's two time columns, time sub 10 and time sub 1, which is equal to t. So what's that about? Well, time sub 1, that might be like the time to swing back and forth once. Oh, I should have defined that for you guys. Time period actually is the time they go from the left side back to the left side again. So back and forth, right, is one full cycle, and the time associated with that is capital T. I should say too that capital T, you guys have seen it in a different context to represent tension in the past. Okay? If you really want to distinguish between the two and have like no ambiguity at all, sometimes you can do F sub T for tension force, right? But capital T in this particular context means time period, right? So time to go from here back to where it started, okay, time period. Right? And what I'm having you guys do is you're going to time, how long does it take to do 10 cycles, and then divide that by 10. And then that time resulting time period will be like the dependent variable, or at least that's how we're approaching this, thinking about it. Okay? Now, remember the advantage of doing it that way. See, if you just try to time it for one cycle, there's a certain error associated with trying to start and stop the stopwatch, but you're not going to hit it exactly at the exact correct points. Okay? But if you time 10 cycles and then divide by 10, then that error of starting and stopping the stopwatch also gets divided by 10. Right? If you do some experimental write-up FRQ in May, then that particular point I just made might pick up a point or two. It's just like, oh, hey, if you time 10 cycles and divide by 10, then the error associated with timing it also gets divided by 10. Okay. Yeah, it might be random error if sometimes you're a little early, sometimes you're a little late on stopwatch. It could be systematic error if you're like always late on the stopwatch or something, but whatever kind of error it is, it's divided by 10. Okay. The next table, let's look at all the tables first so we can get a broad perspective of what's going on. Looks like I want you to control for the mass and the length, but I'm going to have you change out the angle, so that could be independent variable, and then we're relating everything to time, so that's like dependent. Oh, you guys got your cell phones, right? Stopwatches, because I'm gonna need a volunteer here pretty soon to time this for. And then the third experiment, I'm gonna have you control the angle and the length of the pendulum, but change out the mass. So mass is gonna be independent variable, and then how does that affect time period? There's a fourth table here, but it's not really for anything. I guess if you mess up somewhere and you need a like a spare table, then you got that for like a spare. Okay. All right, you guys good so far? Go with us. All right. So who wants to time this? Who's gonna time this? Draw a stopwatch. All right. Yeah, thank you. Right, so let's start with this this third table, change out the masses. They turn my camera. Just see the pendulum swinging right there. Okay. Right. Oh, gotta get some measurements. Now, if you're watching this on the video, I'll have to turn the camera back and forth. You'll eventually be able to see all the data. I have a really long pendulum here. This pendulum is 79 centimeters long. I'm going from the pivot point down to the center mass of the weight. So it's 79 centimeters. 79 centimeters long. I'm going to start it at 30 degrees. Okay. And the particular mass here, well, you know what, since we're swapping out the masses, yeah, this one right here is 100 grams. So let's do that one, 100 grams. Okay. All right. Now the protractor, you guys know how to use a protractor. So just to recap, looking at, I have like a base reference line, which I've got to hold vertical. There's a node in the middle, and then whatever angle it sweeps through is going to be on the outside. So right now, from the vertical, the string is 0 degrees from the vertical. But I'm going to pull it back to 30 degrees from the vertical. Okay, so that's going to be, for the camera, it's going to look like this. The string is going to cross through the node and through the 30-degree mark, which is right about there. Okay, of course, I'm going to do this. This angle. Okay. Right, so ready, Ruth? Right. I'm gonna count off 10 cycles and just tell me how much time it takes. Right, ready?
Yep.
And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. Side note here, right now it's looking closer to about 15 degrees from the vertical. So yeah, it does lose some angle as it goes along. Probably a good thing to keep on something scientific. Right. So how much time did that take?
17.49.
17.49. Right, divided by 10, that's about 1.75 seconds per cycle. Okay. All right, so to swap out the mass, I'm going to go down to, I'm going to throw a 20-gram mass on here. Like that'll be the next one. Keep the same starting angle, keep the same length. Okay. Well, sort of. But I'll tell you guys what, when I swap out a big mass for a small mass, it actually does change the length a little bit. Now it's hard to get it like exactly the same number of centimeters, so we're going to sort of fudge this a little bit, but I'll tell you guys why it won't be exactly correct. Okay. So take off this 100 grammer and put on a 20. That changes the effective length for two reasons. One is that we've been assuming that the string has negligible mass, and that's true proportional to the weight itself for large masses. But if it's a pretty small mass, like 20 grams, well, the string's probably a few grams, so maybe the mass is not all concentrated in the bob like you normally assume it is. Anything that AP throws you, they'll say mass of string. Right? So it's not exactly true. The other reason is that the fact that the weight is physically smaller means that its own center mass is a little bit higher up. So for both of those reasons, the pendulum length itself is a little bit shorter of the recorded number. So not exactly perfectly scientific, but at least we're making notes of that. Right? All right, so pull this back to 30 degrees for 20 grams. Okay, ready?
Yep.
And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.40.
Ooh, 17.40. Okay. Swap this out with 50 grams. All right, 50 grams. Yeah. All right. Get ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.39.
17.39. Okay, let's do 200 grams. 200. Okay, ready?
Yep.
And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.60.
17.60.
What was the mass on that one?
That was 200.
Okay.
All right. And then 500 grams. All right, this is your second biggest lab weight, so it's pretty hefty. All right, ready?
Yep.
Okay, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
18.05.
18.5. So let's take a look at these numbers. All right. So, okay, I need to divide by 10. That would be 1.085. Yeah, I've seen two different rounding rules. One says just always round up. I remember seeing in a science textbook way back in the day that you always round to the nearest even number, which makes like 1.80 instead of 1.81. Reason being, half the time you round down, half the time you round up, and then this kind of evens out. So it looks like we have wildly different masses from 20 to 500. That's a 25-fold increase. But the time period basically didn't change. Right? In fact, if it did change at all, it might have something to do with the slight change in length. Like if I go back and say, like, what's the effective length of this thing? It might not be exactly what was reported because, well, the reasons I told you before. This looks like it's 80 centimeters long. Yeah, we recorded 79. Okay, it looks like it's actually 80, but that might have something to do with it. Okay. Now, later on, near the end of class today, we'll put this in a graph and see what the graph looks like. But you guys can probably see where that's going. It looks like the mass doesn't matter. Okay, you guys see that? Okay. You know what? That might actually be consistent with something that you guys have known since like August, which is, remember the Galileo experiment? Galileo dropped stuff off the tower. Or one of the very first labs you guys did with the cars, right? Same story. In a gravity field, heavier objects have more gravity force on them, but they also have more inertia. Those two effects cancel out. Well, if you just attach the bob to a pendulum, then, well, it looks like it's probably the same story. Like it doesn't matter what the mass and weight was. Like its kinematic motion is the same regardless. Speaking of that Galileo experiment, Galileo was also either the first or one of the first people in recorded history to try to tackle this question we're trying to tackle right now, which is how is the motion of the pendulum governed by different physical variables? I think the story goes he walked into a church, he saw something swinging from the ceiling, and that made him curious about it. And he was actually using his pulse, like his heartbeat, his pulse, as a rudimentary stopwatch, and to start to tackle this question himself. Let's switch over to the next experiment. We're going to change out the angle. So I'm going to keep 100 grams on here all the way down, and I'll keep the same length of 79 centimeters. But let's take the angle, make it 10, 20, 30, 40, 50 degrees. Okay? There's a certain pattern that you guys will see for those numbers, 100 grams back on here. But actually, if you make the angle too big, it starts to get a little wonky. And also, I see on AP write-ups for this particular section, they say whenever you have something like this, they say use like relatively small angles or angles less than, I forget the number, like less than 30 degrees or something. So yeah, 50 is kind of the upper limit to show what we're trying to show here. Yeah, yeah, you could, I guess, go all the way up to 90 if you really wanted to explore that science too. But yeah, maybe we'll do that in class just for fun. All right, so let's go 100 grams right here. But we'll start with the small angles, which are like the proper angles to use. All right, ready?
Yeah.
All right, back to 10 degrees. Okay, and 10 degrees from the vertical. Okay, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.41.
17.41. Take this to 20 degrees from the vertical. Okay. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.49.
17.49. 30 degrees. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.48.
17.48. 40 degrees. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
17.89.
Okay. And 50 degrees. All right, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
18.29.
18.29. All right. For fun, let's try 90 degrees to see what happens. I haven't done this all day, but since you guys recommended it by popular demand, 90 degrees from the vertical, that looks pretty horizontal, right? I was not gonna say it that way, but okay, ready?
Yep.
And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
18.5.
18.5. Right. The angle, by the way, is decreased about 60 degrees now. But, okay, 18.5. 5. All right, so let's go to this. Looks like, well, as the angle increased from the vertical, the time went up a little bit, but hardly at all. Like it's pretty flat line. Like it's probably going to be another node relationship. I'm thinking. Well, we'll see for sure on the graph, but I think that's how it's going to turn out. All right, so we've done 2 of the experiments, and both of them are looking like no relationship so far. Huh, that's interesting. What about length? So this is the last experiment we have to do. How does the length matter? So let's start with 100 grams, 30 degrees, 79 centimeters. You know, we've actually got this data point a couple of times already. Got 1.48 and 17.48 and 17.49 seconds. So just use 17.49, 1.75. Okay, because we've already measured that twice and got pretty much the same thing. So I need to make this pendulum shorter, and write the data on this. Pick up a few centimeters at a time. All right, what's the length of this guy? All right, from the center mass up to the pivot point, 63 centimeters. 63 centimeters. All right, ready?
Yep.
And Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.82.
15.82. Ooh. Look a bit more interesting. Some kind of relationship going on here. That's not gonna be enough of a change. Let's see what this is. 57. Yeah, let's do it. 57 centimeters. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
14.96.
14.96. All right, got 48 centimeters. 48. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
13.72.
13.72. That should do anything. Let's see. Oh, yeah, let's use this. This is 38 centimeters. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
12.09.
12.09. Gonna throw in one last one here. Let's do a real short one. Okay. So, yeah, this real short one could help us out on the graphs, especially. This is what, 20 centimeters. 20 centimeters. All right. And go. 1, 2,
Oh, can you?
3. Oh, yeah. Let's start. Okay, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
8.71.
8.71. All right, so see, for decreasing pendulum length, they were decreasing time periods. So I got pretty small right there. All right, so we've got all the data that we need for this lab. Now we just got to make the graphs and interpret those results. All right, so if you flip over to the other side, well, there's spaces for some graphs. Yeah, if I was designing this from scratch last night, I'd probably blow up these graphs a little bit, but you guys got two small ones, a big one, and then some blank ones we'll talk about later. So the first small one, time period versus mass. Let's go time period in seconds versus mass in grams. Okay. So that was the first first experiment that we did. The biggest mass was 500 grams. So I have to scale the horizontal axis up to 500. So yeah, I have to do it that way. 0, 0, put 500 right there, something like that. And then the time period in seconds, that was pretty consistent. The biggest number is 1.80, so pretty much goes up to 2 seconds. So 0, 1, 2, 0, 1, 2. Okay, so that should contain all the data. Now I'm going to plot these like Cartesian points. But you guys remember the title of the graph always gives away what goes on which axis, right? So t versus m, it's like y versus x, so time period versus mass. So that was for a mass of 100 grams, time period was 1.75. So 100 grams, 1.75, that's right there exactly. 20 grams, 1.74, and 50 grams, also 1.74. So 20 grams, 50 grams, those points. 200 grams, 1.76, 200 grams, 1.76, and 500 grams, 1.80. All right, so there you go. You guys see basically a horizontal graph. Maybe has a slight upslope to it, but you guys just saw from that very last experiment that longer pendulums take more time, and swapping out the mass did actually affect the length a little bit. Okay, so that's probably the reason why it has a slight upslope to it. But other than that, it's basically no relationship. Yeah, I'm really sure. Okay, so you can put on whatever mass and it should be the same time period, and that would be consistent with the physics that you guys have done since some of your very first labs back in the day. Some particular gravity field, well, it's the same kinematic type motion. Okay, next graph, time period versus starting angle from the vertical, theta. So you got t in seconds versus theta in, say, degrees. That was, well, the angle, well, we'll go up to 50, but we did do a 90. See if we can put that on here. Do this way, 0, 10, 20, 30, 40, 50. Yeah, okay. I think I'll lose that 90-degree one, but it'll be all right. The time periods were pretty consistent again. The biggest number is 1.85. So I'll scale this time axis the same as I did the other one. Time period 1 second, so 0, 1, 2 seconds. And let's plot those points. Got at 10 degrees, 1.74 seconds. 10 degrees, 1.74 seconds. At 20 degrees, 1.75, 30 degrees, 1.75, 1.75, 1.75, points right there. At 40 degrees, 1.79, 40 degrees, 1.79, 50 degrees, 1.83, okay. And then at 90 degrees, which is, where would 90 degrees be? 60, 70, 80, 90. Actually, I might be able to squeeze it on here barely. It's 1.83, it's like right there. Okay, do you guys again see basically a horizontal type relationship? So no relationship. Make the angle whatever, and time period does not care. That one I personally think is most surprising. I would have hypothesized differently, but hey, that's how it bears out. So the time period of a pendulum has nothing to do with the angle it's swinging at. And then this last graph. Now this last graph is blown up a lot bigger because this is one we're gonna get kind of interesting results. Time period in seconds versus length in centimeters. Okay, last experiment that we did. See, the biggest length was 79 centimeters, so I better scale it accordingly. 0. Yeah, let's go. I think I'll do 5 centimeters per tick mark. So 10, 20, 30, 40, 50, 60, 70, 80. Okay, yeah, that was perfect. Contain all the data. And then the time period, well, biggest one's 1.75 seconds. So let's see, 0, 1, 2. Okay, so it should all be in there. All right, so Cartesian coordinates again. So like x, y values. So at 10 degrees, or sorry, wrong table. Right? Okay, at 79 centimeters, it was 1.75 seconds. 79, 1.75, right? 7.5, so right there about. Okay. At 63 centimeters, 1.58 seconds. 63, 1.58, right about there. At 57 centimeters, 1.50. 57, 1.50. At 48, 1.37. There. 38, 1.21. 38, 1.21. And then at 20 centimeters, before I plot this last point, we got those 5 points so far. How many of you guys think that at a glance, that looks pretty linear? Think that looks pretty linear? Now, if you did assume that, then maybe you were to like extrapolate backward. Right? Extrapolate backward. So like, okay, that looks like a nice line best fit right there, right? So, all the way back. And if it actually does continue linear all the way back, then that means that for these really small lengths, like as the length approaches 0, it would approach some definite swinging time. You start to think about that logically. Does that really make sense? Or do you think it would make more sense that as the length approaches 0, the time period probably should also approach 0? Okay. You know what? We're running into a situation that we've run into a lot of labs in the past, which is that at a glance, the numbers look, the relationship looks linear until you really stop and think about it. Think, well, I wonder if this is actually part of maybe some kind of root curve, maybe something like that, where it just looks linear if you're like out on the tail. Right? Okay, so let's plot that last point and see if that, which story this is consistent with. I mean, I don't know, I haven't plotted it yet. I'm just doing it as you guys are doing it. At 20 centimeters, 0.87 seconds. So at 20 centimeters, 0.87, that lands right about there. Yeah, okay. You guys see it kind of like curving down? Okay. And if we did an even shorter pendulum, then it should be consistent with that story. Okay. So it's going to do something kind of like this, where it has kind of a curve to it. Okay. Now, how many guys are looking at that curve thinking, I think that looks like it's probably part of maybe a square root curve? How many guys think it's probably a square root curve? Yeah, I think that's probably going to be the case. There are a lot of equations that have worked out this way in the past. Okay. But if you want to know for sure, like how do you know it's not, say, like a cube root or a fourth root or something? Right? Well, this gets into but we're going to use a trick that we've used in the past and that AP also likes, which is axis manipulation. That's why I left a couple of blank graphs here. Also why in these tables I left a blank column so you could like fill in an extra calculation if you have to. Sometimes AP does that too. They'll give you something like this, and then they'll give you a blank column and you can make your own calculations. Right. maybe I want to square root something or square something, depending on which way I'm going. And either of those could be options. And I'll remind you guys why. So I'm just going to go back and do an algebra recap. Let's say you have something like, I'll go real basic just so it's really apparent what's going on. Okay. X, Y values. Okay. And maybe your X values go like 0, 1, 2, 3, 4, 5. And your Y values, I shouldn't have done that. Okay, I messed this up. Sorry. Because I want my example to look kind of similar to what we're doing. Okay. So X, Y values. Okay. Maybe your Y values go 0, 1, 2, 3, 4, 5. Your X values are like 0, 1, 4, 9, 16, 25. Now my numbers are like too perfect. You see exactly what's going on. If this was like actual data or even an example that AP gave you that involved data, it might be like 8.5 and 17.3 and like 24.1, right? Numbers that are kind of close, but not exactly. Right? Okay, so what would this look like, say on a graph? So X, 5, 10, 15, 20, 25. Y, 1, 2, 3, 4, 5. Okay, plot these points. You've got 0, 0, you've got 1, 1, you've got 4, 2, 9, 3, 16, 4, and 25, 5. Okay, might kind of a weird angle. I don't know if those are exactly where they go, but pretty close. And basically like a square root type relationship. Okay. So the equation of this is y is equal to the square root of x. Okay. Did you guys see that? Okay. Right. Now that's knowing the data and the equation that fed into this, and you see the graph. But in our pendulum lab, we're approaching it sort of from the opposite point of view, which is that we have something that we suspect is a square root, but we want to confirm that and see if that's the case. Okay. So I showed you guys this trick, and we've used it a few times in this class already, of axis manipulation. Like there's two ways that you could possibly manipulate the axes. One way is that, see if y is equal to x squared, for example. Okay. One way you could do this is you could plot y versus the square root of x. The other way you could do this is you could square both sides and do y squared versus x. Okay. And well, you guys try this yourself if you want. I mean, you guys have seen this before, so I'm too detailed about this, but whether you do y versus not x, but the square root of x, or again, not y versus x, but y squared versus x. Either way, these will line up into like an exact straight line. Actually, we'll go ahead and plot that. So y versus the square root of x, that means these numbers would be exactly the same all the way down. Like the square root of 25 is 5, square root of 16 is 4. So you got 0.00, 1, 1, 2, 2, 3, 3, 4, 4. Okay. And then those would obviously line up. Okay. And the fact that they line up into a linear relationship tells you, I manipulated the axes in such a way to confirm that the original relationship was a square root relationship. Okay. Alternatively, if you want to go ahead and square the entire y column, you'll get, go back to this table, 0, 1, 4, 9, 16, and 25. So the numbers would still match, just in a little bit different way. 0, 0, 1, 1, 4, 4, 9, 9, 16, 16, 25, 25. Okay, so it'd be like kind of spread out, but it would still lie on a straight line. Okay, so if we suspect a square root curve and then we follow accordingly, and we get something that lines up where all the points like line up in a straight line, that would be a good confirmation that there was a square root relationship to begin with. And that's what we're dealing with here. I'm suspecting this is a square root relationship, and we're going to see for sure. Okay. Guys got that? Tell you guys what, that is as far as I've been getting in classes today. So I know we have like 10 minutes left in this, but it's kind of a weird PowerPoint. But I think it's a workout because you guys hold on to that lab, come in the first day tomorrow, and you'll get to see this one more time, having slept on it, fresh perspective. We'll finish this lab and then we'll go into harmonic motion demos.